Some ship hull bottom panel components are selected and placed into a sizing group. This active sizing group is composed of 11 components. Each of these sizing panels can be optimized individually. Component 548 is made active. The sizing form is synced up to the active component. It belongs to the uniaxial stiffen family. There are many panel concepts in this family, but the only concept we are considering here is the inverted T-shape. The Variables tab displays optimum cross-sectional dimensions. For this panel bay, the optimized panel height is 6 inches. This height variable is set to optimize the range of variables with a minimum equal to 4, a maximum equal to 6, and 3 trial permutations. This box displays the optimum value, as does the label on the figure. Optimum values for stiffener spacing variable, bottom flange width, bottom flange thickness, web thickness, and top face thickness are noted. The steel material system is easily linked to the analysis. This tab displays the modulus of elasticities. This tab, the stress allowables. Note the skin has 23 permutations of thickness. All possible combinations of variable permutations generate candidate designs. The lightest candidate, number 1123 out of 2484, is found to be optimum with a unit weight equal to 18.5 pounds per square foot. Candidates are evaluated for all potential failure modes to all applied load cases. The lightest candidate that meets all criteria is the optimum. The candidate's critical safety factor, or minimum margin, is summarized. Buckling modes are now being displayed for each panel bay for its controlling load case. Clicking the icon causes results for the other panel bays in the group to update real time. There is 1 half mode in the longitudinal direction and 8 half modes in the transverse. This is caused by the relatively high compression load in this direction. Loads for these panels are extracted from the FEA, and their values will be discussed later. These buckling solutions are not performed with FEA. They are being done independently of the FEM mesh, which is how variables, such as stiffener spacing and heights, can be evaluated dynamically. The Rayleigh-Ritz energy solution is extremely fast and allows Hypersizer to analyze panel buckling to thousands of candidates and hundreds of load cases for a quick optimization turnaround. The Show Component Optimal cross-section is displayed. The legend to the right lists the unit weight of 17.2 for this design. Clicking the icon again causes results for the other panel bays in the group to update real time. The optimum cross-sections are those most suitable for each bay. In general, the panels are smaller and lighter in the middle. The resulting designs are sized to carry the computed FEA forces, and though the forces are representative of ship loads, they are dependent on the FEM approximated applied external loadings. Therefore, the Hypersizer computed optimum plate thicknesses may be thinner than actual production hardware, while also not meeting standard minimum gauges. The optimum cross-section variables for panel 548 can be reviewed from the Variables tab. These combinations of dimensions produce a panel that has near zero margins of safety. The other active components in the group also have near zero margins. The Failure Analysis tab lists the analyses performed. Several panel buckling analysis methods are toggled on and display margins. For this panel, the lowest margin is caused by the buckling method highlighted with the blue circle. This is a method that includes biaxial loads, shear loads, and transverse shear flexibility. The stiffener buckling flexural torsional, also known as tripping mode, is displayed. Next are the local buckling margins, crippling, and material strength. We can isolate individual objects such as the web or skin. Margins are shown for limit loads using yield stress allowables and ultimate loads using ultimate stress allowables. By including all failure modes and sorting the results, all of the failure margins are easily established. For this panel, the controlling failure mode is local buckling of the clear span. Different panel bays optimize to different skin thicknesses. If the optimizer is allowed to size the skin thickness as a continuous variable, component 548 has an optimum thickness equal to 0.2955. The weight of each component in the group is summed together with a value equal to 16,935. Instead of allowing free sizing of each panel bay, we will impose our first manufacturable constraint. The skin is now required to size to a discrete plate thickness that is readily available in stock from a vendor. Stock sizes are applied to this steel alloy. This material is available in these thicknesses. We will not consider any plates thinner than 0.25. The optimization is now started. The video is running at actual recording settings for you to see the real-time optimization speed. The results are now viewable. Now the skin plate thicknesses are 0.3, 0.275, and 0.25. The updated weight is 17,162. The optimal stiffener spacing is different for the individual panel bays. This component has a value equal to 14, while this is equal to 12, while others in the group have a value equal to 10. In order to keep the load path down a straight line with no force eccentricities, we select to link the stiffener spacing variable. By optimizing the group, the lightest weight of components have a common spacing equal to 10. The weight for the group is 17,431. To further the manufacturability of the design, you may want to link all variables of the stiffener for all panels of the group. This means there is one stiffener shape and size for all panels. As expected, the weight penalty is substantial, with the group weight now equal to 20,277 pounds. The graphics show this constant design for all panels.